Welcome back, guys. Today we're going to discuss about surface tension and the interfacial phenomena, and also we are going to do a couple of calculations on hydrophilic lipophilic balance. As we discussed in the class, surface tension is force per unit length. Okay, force per unit length applied parallel to the surface to counterbalance the net inward pull. I'm going to explain you take a look at this. So let's assume this is a beaker and these are the water droplets. Okay, so for example, this particular water droplet, okay, so it is experiencing the pull from all directions, right? So it's experiencing pull from all directions. So overall it will be like pretty stable. And what these molecules, what about these molecules which are on the top of the layer, these molecules, okay, what is happening? This molecule is being pulled by this particular molecule, right? And also over here, so all these molecules are trying to pull these molecules down, but there are no molecules on top of here, above this layer. So overall this particular molecule here is experiencing more pull towards downward rather than equally pulled all over the other sides. So let's take an example of this particular molecule here. So this molecule is experiencing a higher pull downward. So to counteract this net inward pull, okay, this has to apply a force that is parallel to the surface. So how it can counteract the balance? So it is directly dependent upon these parallel forces, right? So that is what the surface tension is in detail. It's force per 1 unit length. Let's say this is 1 unit length, okay, applied parallel to the surface. This is parallel to the surface, right? This is parallel to the surface to counterbalance the net inward pull. So to counterbalance this net inward pull, so it is applying force over here. It's like, let's assume as a person, okay, if this person is in the air and holding two rods, so his gravitational force is acting downward, right? So if he has to stay in the air without falling down, what he has to do, he has to apply force parallel. So he has to hold it tightly, this rope. So that is what is happening for this water droplet now. So that is in a different way explaining the surface tension. Anyway, let's get back to the interfacial tension. Interfacial tension is force per unit length existing at the interface. What do you mean by interface? Let's say this is some media, like some liquid, or some liquid, and this is, let's say this is water, okay, this is water, okay, water and some liquid, we don't know. So here, if you observe carefully here, there is, I'm sorry, here, if you observe carefully, there is a layer, right? I mean, there is an interface between these two layers, right? So there exists tension at this interface because these two are immiscible liquids, because this is oil, okay, this is oil and this is water, okay, these are two immiscible liquid phases. So there exists an interface between these two immiscible liquids. So the force per unit length, again per unit length, let's say this is 1 unit, force per unit length existing at the interface, this is interface between two immiscible liquids, is called interfacial tension, right? So let's get to surface tension and surface free energy now. Okay, so okay, as you all know, the surface free free energy, the definition is the increase in energy, in potential energy with increase in surface area is surface free energy. In the other words, it's a work that must be done to increase the surface by unit area is surface free energy. Let's say if I have a water droplet, okay, and one second, what's happening? Let's say if I have an oil droplet, okay, this is an oil droplet. What if I break this oil droplet into two pieces, into two small pieces? What is happening now? You can see there is an increase in surface area, right? Initially the surface area is, let's say this is 10. Now I'm breaking into two pieces. Now this particular area is exposed, so there is an increased surface area. Let's say that the increase in surface area, it could be like 15 roughly, let's say. So there is an increased surface area. According to the formula which you may see here, or the definition, there is an increase in potential energy with increase in surface area is surface free energy. So here what is happening, A, the difference in area is increasing. Can you see that? The A is increasing. Obviously the surface free energy or work is done is increased. So W is equal to surface tension or the interfacial tension times delta A. Okay, so let's say in suspensions or in emulsions formation, we are going to discuss this again. So there the formula will be that delta G is equal to delta SL times delta A. That's how we're going to discuss, because S and L is nothing but oil is L and S is water, right, as we discussed in the class. So this is the surface free energy discussion in brief. And what, so how we got this formula, how we got this surface free energy formula? Let's try to find out the formula how we got this. As you all know, surface tension formula is force per unit length, right? Force per unit length. But we know the definition of work, and its formula is force times displacement. Displacement, ds, displacement. Okay, so the difference in work and the difference in displacement, and this is force. But according to our surface tension formula, F is nothing but surface tension times 2L, right? Now if we replace this into this formula, what is the formula now? W is equal to surface tension times 2L times displacement. We all know the area formula, right? Area of the formula. Area formula is what? Length times breadth. So let's replace this particular part with area. So W is equal to surface tension times area. So it's the area is what? It's not a newly created new area. It's an increased area, right? So that is a difference in area between the old area and the newly created area, because you're breaking the particle in the water droplets in detail. So it's delta A. So